spend one moment before I get into the main topic of the lecture. Oh, this is not advancing. I might have to do it the old-fashioned way. Oh, maybe it's here. Let's see. And I want to talk a little bit because you guys have just been through the grinder of applying for college when everyone gave you the impression you're supposed to know what you want to do and then go do it to be a successful person. And so I want to start just briefly and tell you my trajectory from the honest way. Not the way people put it in the bios that they write down, but the way that things really happen. And the way that things really happen is every choice I made to do something, the basis on which I made that choice was not what turned out to happen. And every opportunity that came was not one that I could plan for. It was one I had to seize in the moment. So I want to just take you quickly through that trajectory, that ladder here. So when I decided to go get my PhD, I thought I was going to study the behavioral ecology of shorebird mating systems. I was going to watch shorebirds have sex, and especially a species called spotted sandpipers, where the females were aggressive and the males did the parental care. And that was my plan. What I wound up doing, and I was going to do that in Minnesota, by the way, and what I wound up doing was studying the conservation of biology of how shorebirds respond to fragmented wetlands in a drought. It was the last major drought before the most recent major drought in the western United States. And the key thing that happened there is I started making my own maps because the maps of the wetlands were inadequate because they didn't tell you where the water was when. Then when I came for a postdoc, I came to the University of Houston. I was going to do a 2-year postdoc to study how marsh rice rats in coastal marshes respond to hurricane storm flooding. What I did was, as you heard from Bhavya, I met colleagues at NASA and my future husband in Houston and decided to stay. So I wound up in the NASA orbit even though that was never in my plan. Then what I thought I was going to do when I got hired was train astronauts in ecology before they went to Mir, so that when they went to the Mir space station and took photographs, they would understand the Earth below them for that 4 to 6 month stay. What I actually did is I got a major grant to develop the Millennium Coral Reef Maps and to work with developing nations to use those to manage their local fisheries. So I had a lot of NASA or science funding. Then the chief scientist of the space station at the time came to me and he said, hey, you know, you cover a lot of different science disciplines, biology, chemistry. I've heard you lecture and I think you do a great job. Why don't you come and spend a year with me, just 1 year, and then you can go back to your research. But why don't you come learn how the programmatic side of science at NASA works and help me get the International Space Station started. By then we were just starting to assemble it. We were doing a couple of experiments every 6 months, maybe 6, because we were mostly building it. And so I went to work for him. That was astronaut Don Thomas. And what wound up happening is I wound up staying and spending over 12 years as his successor as the chief scientist for the space station. Then I decided, you know, I've solved these problems. I'm on my 3rd program manager in the space station, and I think I'm ready to solve new challenges. So I went to the human research program and started setting up what we call the Moon to Mars strategy, which is the strategy for how we would use our human research on the space station, the future human missions to the moon under Artemis, to prepare for the first human mission to Mars and solve all of those biomedical challenges. And I thought that that was my path in. I was part of their succession plan, and I thought I would probably direct the human research program. But when it all came down to it, I was one of 2 final candidates, and I was not selected. But I got the opportunity to go to the Artemis program at NASA headquarters, and so throughout COVID, I was setting up the science requirements and processes to make sure we did good research in Artemis, which it turned out they had not set up those requirements when they were actually building most of the hardware, like Orion and SLS. So we had to cram them in after the fact and set the requirements for the rovers and things. And so that was really successful, and I trained up a successor who was a planetary scientist, but I thought to myself, you know, this discipline isn't the same for me. I'm not feeling it the way I did for all those years in the space station. And then an opportunity came out about a year ago to go to NASA Earth Science. So now I am working on making sure that our NASA Earth Science missions help society respond to climate change. So each of those steps along the way, now that I'm home with my discipline family in some ways, but each of those steps along the way was essentially unplanned. When I did have a plan, it didn't work out. When I didn't have a plan, amazing things came. Of course, I always had a short-term plan, like it made sense to take the job or become the civil servant. So it wasn't like I did anything bad, but I also never did exactly what I intended to do. And I think that is actually the trajectory of most careers. So I think it's a very rare person who does, there are very few people in this room that will be doing what they think they're going to do in the future. And I just wanted to share that with you because I think you're put under a lot of pressure. And my own daughter's 21, she's just been through this same grind, and it's wrong. If people tell you that you're going to do what you want to do now, or what you think you're going to do now, they're misinforming you. So now let me get on and talk to you about my original topic. So this photograph was taken from Apollo 8 in 1968. And this was the mission with Frank Borman and Jim Lovell and Bill Anders. And this shot was iconic. This was the first time that humans observed the Earth rising above the surface of the moon. The picture's called Earthrise. And it had a transformative effect in society. Of course, people were following the Apollo missions so closely. This was a huge matter of American pride, a huge matter of global interest. And suddenly we saw the Earth as a little blue dot, as something very precious, something very far away, something very contained, and something potentially vulnerable. And there was another iconic image that came a little bit later. This image was from the Apollo 17 crew, and in this case, we had our first actual practicing scientist on that crew in Apollo 17, and that was Harrison Schmitt. And that image is called the blue marble image, and that also was transformative for people as they realized how small the life support system of the Earth was. And in fact, I spent much of my time in the 70s watching public television. I loved Electric Company, and I loved the Big Blue Marble. And that particular show was all about how small the Earth is, and it set up pen pals and things around the world because there was an emotional response to realizing that the Earth was a small place and that all those boundaries that we see with each other, those social and political boundaries, are actually not that meaningful if you think of the Earth as a planet as a whole. So human spaceflight and the Earth as a study both have come together over the last 50 years. And in fact, NASA has spent a huge amount of that time studying the Earth. People don't always realize that because sometimes the Mars rovers get more press or the astronauts get more press. This is our Earth fleet right now. We have 24 satellites that we're operating in orbit around the Earth, each of them making a unique measurement to help us understand the Earth as a system. And so this is our Earth fleet overall. The way you read this chart is the spiral. The things on the inside are the oldest, and these satellites age and they have to be replaced. So about half of our $2.2 billion budget at NASA for Earth science every year goes into building and replacing this fleet, and especially advancing the technology in this fleet so that we keep making better measurements and measurements that help us understand the Earth more precisely. There's also two different, let's see if you can see the little arrow there. I don't know if you can. The inner band are the instruments on the International Space Station. So one of the really cool things I got to do was develop the approaches to help Earth science first start putting instruments on the attachment points on the International Space Station. They didn't dare do it until we got done assembling it because they were afraid somebody would ask them for part of the money to build it. So they stood back and wouldn't use it at first. And then when the space station assembly was completed, I worked with my Earth science colleagues at the day to get those instruments on board. And we have 7 on the space station today, and we have 1 more being built. And so just a few months ago, I had the opportunity of getting those extended throughout the end of life of the space station in 2030, which was really kind of fun to see 2 pieces of my career come together. And then the instruments, as they turn orange, that means they're just operating in their initial mission life. The ones that are in blue and green have been extended. And then the ones in yellow out at the back end are the ones that we're trying to develop, which means we have to negotiate with Congress and the Executive Office of the President to actually get the funding for those missions and define all the requirements and make sure that they're going to meet the needs that we've identified for studying the Earth. So in our Earth System Science Organization, we do 5 things. We advance the technologies, and we build all of the missions for NOAA and for the USGS. So NASA even does the project management and builds all the weather satellites, even though they're operated by NOAA. And we build Landsat, even though it's operated by the US Geological Survey. We also advance the technologies so that the missions keep getting better. They keep making more precise measurements or more relevant measurements. Then we build the satellites, we fly them, and operate them. We fund the research and analysis, so we fund a big extramural research program where faculty apply for grants, and so any of you who wind up in this discipline, if your professor has NASA funding, he got it from us. And we also fund intramural directed research within our NASA scientists. Then we advance the data and computing architecture because a lot of the global models and the global data sets I show you are very computer intensive. So we have massive models that help us understand the Earth as a system of systems. And as a biologist, I honestly think of this very similarly to the way I thought about the human body when I was doing work in human research. The human body is also an incredibly complex system of systems that has all of these synergistic effects and all of these unknown effects. When we tweak something, weird things happen because we don't understand the system completely. And so it actually takes the same kind of thinking and sometimes the same kind of like digital twins modeling and things to try and understand this complex system. And then we do applications where we try to make that information useful and usable by people who are not Earth scientists. So let me start with this and just really talk about the Earth as we see it at NASA. So this image shows you a compilation of aerosol optical depth with the spectrometry to define what the different things that are interfering with the view of light as it penetrates through the atmosphere are. So in orange, you see carbon dioxide, and you can see fires burning. In that, or sort of red, the darker red, are fires burning. You can see some fires in Australia. You see some fires in equatorial Africa and some fires in Asia. In that green color, you see the sulfates. Sulfates are primarily a product of combustion in the northern hemisphere. And there's actually a seasonal pattern there where you get that combustion that happens in the winter as people cool and heat their homes. And you see a lot of it coming off of Asia where they're using things like coal that produce a lot of sulfates. Then you can see in pale orange the dust coming off the Sahara, blowing all the way across the ocean to Africa. In the pale blue, you can see sea salt actually getting up into the atmosphere, primarily over the oceans. And then in pink, you see the nitrates, also a product of combustion. And right there, we're in the winter season, and you see all those northern hemisphere developed areas with nitrates. And the most important thing you see here is that it's not separated. So today in our society, we use laws at national levels to try and regulate pollution. And the fact is, it's global. And we just saw that. Those of us who live in the Northeast, either New York or Washington, D.C., just had Canadian wildfire smoke come in. New York City had the worst air quality of any city in the country for almost 3 or 4 days in a row. And that is because these patterns are global. And in fact, you can see some of the wildfires that happen during the period of this particular modeling and assimilation run. So I think of Earth systems, and you can divide or kind of categorize the Earth as a system in a bunch of ways. But one way that I like to think about it is very simple. We've got the atmosphere, the biosphere, the lithosphere, the solid Earth processes, the hydrosphere, the water, and the cryosphere, the frozen ice. And we've got the radiation from the sun coming in. So at its simplest, you can think of the Earth as being driven by the radiation from the sun and then all of the interactions of these systems together. Well, it turns out, as I think about Earth science, as I mentioned, I also think about the life support and the things we've been trying to study on the International Space Station to prepare humans to go to future missions to Mars. And we've made huge advances in understanding how to keep crew members healthy when they're in space. And it turns out the systems are really the same. And that kind of makes sense because on the Earth, the things that a human body needs to live and have this be our great home planet are the same things you need to reproduce if you're going to have a spacecraft be your home for 6 months or a year. So you've got to recycle your air, you need food, you need a place to store stuff, you need a cooling system, a reservoir for heat and cold, and you need to recycle your water. And once again, your power is coming from our friend, the sun. So these systems are not that different, even though they're at very different scales. So this is the winning concept. I love that they won the concept with a drawing like this, by the way. That's pretty cool. That would not happen today. But this Hamilton Sunstrand, which is now United Technologies, won the concept for the Apollo life support suit with this closed-loop system in 1962. And this was their design. And that led to the development of the Apollo 11 suits. That suit is one that you can go see at the Smithsonian. If you go to the Air and Space Museum, that's there. And on the back, it had this PLIS, the Portable Life Support System. And that PLIS does all the atmosphere and water recycling, and also there's a thermal garment underneath it to help keep the astronauts cool so they don't cook up inside that high. They have to be very insulated because space is very cold, but then they start building too much heat, and so you need a thermal regulation system. And then that top, the OPS, the oxygen purge system, is the backup, because if something goes wrong and the system quits working, you need enough oxygen to walk back to the spacecraft. In fact, I spent much of my 2 years in Artemis trying to figure out how to let the crew get away from the landing site with a rover, but if they had to walk back, they couldn't go too far. So if you can only go as far away from the landing site as you can walk back, then why build a rover if the rover can only take you as far as you can walk anyway? And that was actually a huge conundrum. We spent hundreds of hours of meetings trying to figure out how to get the astronauts to geologically interesting places and still do it safely. And then on the right here, you see the new Artemis suit that was recently announced. It has its dust cover on it, which makes it look cool and black, and it was built by Axiom Space. So this is the latest suit and what that's going to look like. So the International Space Station, where I spent a lot of time on my career, and this particular view I really like because it shows you how shallow that protective life support system is for the Earth. So in the astronaut suit, right, there's that thermal barrier on the outside. On the Earth, there is also a thermal barrier, and those are the gases of the troposphere. And so this system is very, very similar to the life support systems of the Earth. So, you know, and just to give you a little more detail, we have what we call ECLIS, which is environmental control and life support systems. That includes our life support, our environmental monitoring, our fire safety, and our logistics, things like clean t-shirts, because you don't wash clothes in space. You wear them for 5 days, and then you throw them away. And then our crew health and performance systems, which includes the spacesuit physiology, monitoring heart rate and so forth when they're doing really intense physical labor. The countermeasures like lifting weights so that they can maintain their bones when they're in space for 4 to 6 months. And of course, for a Mars mission someday, we've got to have a set of exercise countermeasures so they can maintain bone for at least a year on the trip to Mars, so they're strong when they land on Mars, and then work really hard in heavy suits in 3/5 G, and then they're going to come home once again in microgravity for 12 months. We've got to protect them from radiation. We have our medical systems, and we have to provide food and nutrition when some vitamins are not radiation resilient, so they'll break down in the food. And that's why we do things like plan greenhouses and things where we can grow vegetables that have especially vitamin A in them, which is highly sensitive to radiation. And so all of those things we've been advancing on the International Space Station. We're figuring out the best versions to take and test on the surface of the moon. And then we will take that combination of systems, both the orbital systems and the planetary partial gravity systems, which have different physics, and those will be our test bed for the systems we take for the first human missions to Mars. And this just shows you an example of that. This is the set of oxygen generation systems that we had on the space station. Starting in 2001, when we started, we only had a Russian legacy mirror system called Electron, and you can see the crew member standing in front of that. And then about 2012, we launched and tested our first oxygen generation system that was built by the US, interestingly by Hamilton Sunstrand, and around 2012. And then you can see in 2018, the European Space Agency, those partners, launched a closed-loop life support system to test that they're hoping would be closer to what we might take to Mars someday, and that is in its test phases. And I just wanted to show you a diagram of that to compare it maybe to what you just saw in the spacesuit diagram. Once again, we've got, you know, a cycle of reactions, removal of carbon dioxide via an absorption-desorption process. We've got a Sabatier reaction to catalytically convert carbon dioxide to hydrogen and water and methane. And then we've got an electrolyzer to electrolyze water and give you another source of breathable oxygen. So we are essentially trying to provide a little mini Earth. and it is incredibly energy intensive. So the Earth does all of that for us for free, but of course we're disrupting the balance of some of those gases like carbon dioxide, and that's what's leading to the changes in our climate. We, as I mentioned, we also grow plants in space. So this is an example of some lettuce being grown on the International Space Station. You've got to give it a good, strong light source so it knows where to grow up, because it can't sense it from a gravity perspective. Plants actually can sense both. So you have to overcome any gravity sensing, which is not there, so that they'll grow with the light signal. And then this is Mizuna lettuce, which is high in vitamin A. I think it's kind of bitter, but if it's your source of vitamin A, because your pills will have all broken down about halfway to Mars, then Mizuna lettuce is going to taste pretty good. So I want to talk about the carbon cycle in general back on Earth now. So carbon is carbon dioxide, of course, in the atmosphere. So those purple arrows going down show carbon being built into plant bodies. Then you have ruminants releasing carbon dioxide out of their guts and carbon dioxide coming out of the land. The ocean has a carbon dioxide cycle where carbonates can be dissolved, and the ocean can become a storage area for carbonates, even as calcium carbonate, and that can sink to the bottom. But it can also become a source and release carbonates and bubble them out. And then you've got a set of energy drivers of all of that. If you burn the forest, you release carbon dioxide. If you burn little vehicles, that cute little car driving around the city, that also adds carbon dioxide to the system. And of course, it's that burning of fossil fuels that has allowed human beings to finally become a planetary scale influence on the atmosphere that we live in. So this is just a representation of the atmospheric carbon dioxide, and you can see the time frame. So this is July. We're looking at the summer when plants are growing, and plants are actually incorporating most of the global carbon dioxide. It's not that orange. And we get into August, and you'll watch the seasons change. We get into September, a nice Indian summer around the world. And then you start seeing some carbon dioxide coming off of industrialized regions as it gets colder in October. You see carbon dioxide being released from more and more combustion in the northern hemisphere for heating and cooling. As you get into November, you see the world becomes this kind of massive extra carbon dioxide planet. As we get through December, there's more and more in the atmosphere. And then as we move through, you'll actually start seeing, as spring comes, the carbon dioxide start getting incorporated back into plant bodies. And so it's fundamental that decisions that are made on local bases, like clearing forests, like the kinds of combustion engines you allow, the kinds of cars you allow. You can see now we're at peak. As we head into spring, there's March when the carbon dioxide is the most dense. And then you'll start seeing it, just so you don't get really depressed. I'm not gonna advance it until we start seeing the summer come, and you start seeing that carbon dioxide that's built up across the winter getting incorporated back into the plant bodies. So of course, I think you all know that what those increased carbon dioxide or greenhouse gases do, and that also includes methane, which is a more potent but less persistent greenhouse gas, about 10 times more potent. They trap heat in the atmosphere, so they function like the glass on a greenhouse. The sunlight can get through, but then it bounces around inside that insulating layer and doesn't radiate back out into space. And so because of that, the planet is warming. And this is a methane example on this particular graphic. So that has had an extraordinary effect on the temperature of the planet. This is just the last 20 years. So from the time the time I finished my PhD to today, and where the trapped atmospheric greenhouse gases have warmed the planet. And what you see on the map is the average change in temperature over that time period. You see the 12-month running average in the red line through here, and you see that monthly mean bouncing up and down. And now you know why that bounces up and down. Sometimes you'll hear a climate skeptic say, well, it keeps changing. Look at that bouncy line. That means scientists don't know what they're doing. No, we actually know why that is. It's seasonal change. It's people burning things to keep warm in the winter. So you've now seen where that particular system driver comes from. And this I love. Some of my colleagues that we support at the Goddard Institute for Space Studies at Columbia University built this model which goes clear to 1880. So this is the lifespan of my great-grandparents, grandparents, parents, and myself. And the color of the line, the circle, each circle is the temperature, average temperature across a year. When it's blue, it's cooler than that 100-year average or 150-year average. When it's pink, it's warmer than the 150-year average. So as that line goes around, and right now you can see we're in 1975, 77, and it's mostly white, so it's about the average over that time period. And now you'll see it's starting to get pinker. In 1991, 96, now it's getting almost more red or hot pink. Every now and then there's a cooler year, or there might be a cooler December on average around the Earth. And now you see that red. And so now we're going to turn that image so you can see the pattern over time. And so there's an extraordinary difference. Whatever weather you have experienced in your lifetime as that relates to climate is not the same climate that your parents experienced or the same climate that your grandparents experienced. I actually have my grandfather was a farmer in Utah, and I have his log of the weather because farmers really care about weather, and I have that log. And you look at the temperatures there, and they're nothing like, what he was observing in 1908, 1910 is nothing like the climate in southern Utah for farmers today. Well, where does that heat go? Because if you notice, that number on there was only plus or minus a couple degrees. So it was only a couple degrees on average. And if you thought about that as weather, you would hardly notice the difference, even though the averages are very different. And that is because of the chemical properties of water. So how many of you know from chemistry that water has this amazing ability, this amazing thermal heat absorption ability, right? Yeah. And so the oceans are doing that for us. They are actually absorbing most of the heat that's being retained in the atmosphere. That's why weather is changing, because the oceans are much of the energetic driver of the weather. And so here you can see that ocean heat content. Once again, a bouncy line looks just like the carbon dioxide line, rising at about the same rate between 2000 and 2010. And then it is changing because when you heat a spaghetti pot of water, right, you get convection and you get circulation within that pot as things start moving around by convection, where it's hotter in one end, it mixes to the other. Well, that exact same thing is happening in the oceans, and so those ocean currents are accelerating and changing. So right now, those of you from Texas, there's a heat dome over Texas in a place where a heat dome normally never forms, because the jet stream has split into two pieces, and that's anomalous. That's not been observed very often. And we think that those kinds of changes are coming from, at its core, this change in the ocean currents. For those of you who lived in California over the winter and experienced the largest number of atmospheric rivers ever observed on the Pacific coast in history, that also is driven by ocean heat content, as best we know, because the more heat content there is in the ocean, the more moisture gets into the atmosphere, and then as those rivers flow, there's much more water in the atmosphere to then fall as rain in those atmospheric river events. Well, I talked about the water cycle, I talked about the atmosphere cycle. Now let's talk about the ice. So this is a polar view of sea ice change. Once again, over the last 20 years, and you'll see the seasonal differences. You get a full, I'm going to run that again. So you see the full sea ice, and then, it doesn't want to run again. Let's do that. There we go. And so you'll see that we've had the most minimal Arctic sea ice observed multiple times now over the last 10 years. And they're even looking at the Inside Passage and the possibility of oil and gas exploration in Siberia because of these substantial changes in sea ice. And then what happens is when you have cold fresh water from the sea ice melting and warmer salt water underneath, you get, on the land ice, you start getting erosion of the land ice from beneath. So even when we see that ice view from space, we're not seeing everything. And we use Lidars, missions like Cryosat, to try and see the thickness of the ice, because the land ice begins to erode from underneath, and we're trying to model the differences in the land ice and the sea ice, which is, of course, already floating. So it's not going to raise sea level since it's already floating there. But the land ice, as it melts into the sea, will raise sea level. And this is, we have this amazing set of instruments called GRACE Follow-On. They measure basically nanoscale differences in the gravity of the Earth. And they let us see how much ice is underneath, because the thicker the ice is, the more gravity as the two spacecraft pass overhead. It's almost like a miracle to me. This is one of the most amazing remote sensing techniques we have. And so what you see here is the average mass loss of the Greenland ice sheets and the average mass loss of Antarctica. Here we're getting up to 2018 or so, and those red areas are the places where there has been massive loss. And if you turn those into curves over time from 2002 to 2020, which is when we've had these missions in orbit, you can see the massive loss of mass, and that actually is enough to change the gravity of Earth as the spacecraft pass overhead. Well, what does that mean for us? It means that as sea level rises, we see real increases in the sunny day flooding. So those of you, maybe there's someone here who lives along the East Coast in Hampton, Virginia, or Long Island. There is more sunny day flooding now than there used to be. There are islands in the Pacific where people can no longer safely live because there's too much flooding there, and they're having to evacuate some of the small islands due to relatively small levels in sea level rise. Then, of course, when there are storms, which is back to the thing I went to Houston to study in the first place, what happens when the storm tides come in with a hurricane, those storm tides are also higher. So that's we see two different changes that are possibly, but not confirmed, to be driven by climate change. One is a change in the sea level and how that influences the flooding as the storm tide comes ashore. And the other possibility is that hurricanes are actually getting stronger because there's more energy in the ocean that drives higher levels of convection. And so recently, those of you who live in hurricane zones know that there have been some really rapid intensification processes that have happened where, you know, it's a category 1 and it's 24 hours out, and then suddenly it's category 4 going ashore. That didn't used to happen. And we just launched a mission called Tropics just a couple of weeks ago that will be some CubeSats that make really detailed measurements of the eye wall replenishment cycle in hurricanes, so we can try to understand that better and actually make measurements of the energy itself in the eye wall replacement. And we're hoping that that will give us more definitive information about whether it is the energy in the ocean that's driving that rapid intensification. And this is just another example. This is the seasonal precipitation variations. So one of the things you get is you get rain where you're not used to it, and you get lack of rain where you're not used to it. So these swings, anytime you take a system of systems and you poke it somewhere, you push a driver in one area, you get responses in other areas that you may not anticipate. So sometimes you think you know, and you try that, and it doesn't pan out. Sometimes you don't know, or you think it shouldn't have an effect, and it does. And so this is the kind of system that we're discovering as we get more and more information about the Earth. For those of you interested in medicine, medicine is the same thing. You've got a body that is a complex system of systems, and something happens, some kind of driver, whether it's an infection or an injury, and then you see impacts across the system that you may not expect. And so it's not unlike that. We also do projections trying to understand what are going to be the effects on society of these changes in the future, not just to be gloom and doom, but so that we can actually help people make better decisions. And I call these projections because these are projections of wheat yield and maize yield across the next 100 years. And the reason they're projections is because they're assuming humans don't do anything smart. So if you just kept planting wheat in the same places you've been planting wheat today, this is what would happen. If you keep planting corn in the same places we're planting corn today, this is what would happen. Now, will humans do that? Absolutely not. They will respond and make changes. We might develop new varieties. There's a whole bunch of things we could do to respond. But this kind of shows you a worst case scenario. And what this shows is really interesting. So, for example, wheat yield goes up in the northern hemisphere because some of the places where wheat didn't grow very well, where the growing season was short, the growing season gets longer, and you can have a summer wheat crop that does better. But when you look at the maize yield projections, Maize is something that already is a hot season crop. That's corn. And those hot season crops are going to hit the limit of what they can do, at least where they're planted today. So you see a lot of red on the maize graph because maize production is not going to do as well as those areas warm. What really makes us nervous, and this is why we use these as kind of worst cases to start understanding, is if you look at the southern hemisphere, the global south, you see maize crops failing, but not necessarily success of wheat, because you've gotten to the point where none of the grains that are grown well, or at least none of the grains that are currently grown in mass, are well adapted to the new climate environment. And so one of the things that this tells us is that our agriculture programs need to work with plant scientists and so forth to figure out what kinds of crops will be well adapted to the conditions in the future. And we also have a set of applications where we work with farmers to get some of our NASA data onto little apps on their phone so they can actually look at the evapotranspiration that they're measuring, they can look at the rainfall that's happened, and make decisions about their irrigation procedures as they go. That can help them save about 25 to 30% of their production costs by being much more efficient with their water and based on the local conditions of the day. And that's important because the rule of thumb that my grandfather used in managing his irrigated farm and his dry farm isn't going to work anymore because the conditions are so much different. And the swings from year to year can be so different that doing more precision agriculture and making informed choices can make a huge difference. So I mentioned that we have a number of instruments on the International Space Station itself that are contributing to our understanding of the Earth as a system. And those are kind of, I feel like they're sort of my special children because I help them get those places to attach and get them up there and then got them extended. And I want to talk about just two of those today. So one is an instrument called Ecostress. Ecostress is looking at the thermal signature. So just to remind you, up here, there are some pictures of a thermal imaging camera, right? You guys have seen those where you can put a thermal imager. There's even some, little things you can attach to your iPhone and do kind of personal thermal imaging, maybe in your spy kit if you want to do that. And this is a handprint that is worked across, and there are different spatial resolutions and there are different thermal resolutions to these thermal imagers. And what we've flown on Ecostress is the best thermal imager technology that's ever flown in space before. And here you can see one of our early images from Ecostress, which shows Las Vegas, and you can see the strip very nicely down the middle. That's the widest road in Las Vegas, and it's covered with blacktop, so it gets nice and hot, and it reflects really nicely. That's that diagonal road across the middle. And but the thing that we can do from that is also calculate out evapotranspiration from plants. So remember, plant bodies draw moisture from the soil up through their xylem and out through their stomata, right? And so as it comes out of those stomata, it cools the plant body. It actually helps the plant cool off as long as there's enough water. Well, what Ecostress can show us is how much of that cooling is happening. And one of the most interesting results that this scientific team had over the last year was they found that they could see plant bodies starting to get hot in drought regions as it got further and further from the last rainfall. So they could detect when plants in California, in the mountains, in the Sierra Nevada mountains, were running out of water in their system, getting dry and hot. And if you've ever hiked in the Sierras, and sometimes you walk into a glen when it's really hot and it hasn't rained in a while, and you can smell that all of the sap smells because the plant has actually finished pulling all the moisture it can find in the soil, and now it's sort of releasing all those resin smells. And so if you've had that experience in hiking in the Sierras, you've actually seen this happen. Well, it turns out that Ecostress can predict where wildfires that spring up are going to be extra hot, because it turns out there can be some areas of the forest or some areas of the hillside where there's a little water left, so the plant body still had a little bit of cooling going on. Those are much less likely to burst into a catastrophic fire than the areas where the moisture has run out and the plant bodies are actually getting physically hotter in temperature. And so this becomes a really important way of predicting wildfire risk, and we're working with our colleagues at the US Forest Service and CAL FIRE to try and take this basically scientific knowledge and figure out how to apply it in a way that the workers in the field, that they could actually think about, do we pre-position fire crews in certain places because we know the risk is higher. So that's still work in progress. But that's how you go from knowledge of the Earth as a system to understanding a specific thing that's going on in the process to actually making actionable information that people can do something about. Another instrument on the space station that is pretty exciting is called JEDI. So JEDI uses Lidar, which is laser remote sensing, to measure forest canopy height and biomass. And so this little picture up in the top kind of gives you a sense of how laser remote sensing works. So you actually shoot a laser from space down at the ground. Kind of cool that we can get to do that. And it bounces off of the trees and the structure it hits, and you get bounces at different levels in the canopy. So you get one big bounce off the top of the canopy, but you actually get additional bounces off the lower parts of the canopy, and then you even get a ground signal. And you can distinguish that using Fourier transform modeling, using basically good physics, and you can get, even from the space station, you can get even single tree information. And so what I've shown you on the left is a California redwood from XY axis, and basically looking this way and then looking this way. And what that laser return signal, once you've deconvoluted it, what that looks like, where you can actually see the structure of the tree. This means you can estimate the biomass of that tree. It's not just looking down and seeing greenness and making a map saying that's a tree. That's what we would do with V-SWIR remote sensing, visible, infrared, and infrared imaging. We'd just see green tree, and we'd see reflected infrared light. But instead, we can actually make an estimate of the overall biomass through that tree. And that helps us to understand the carbon that's being stored in the trees, which is really important, since that helps us know how much laws are actually helping us to store carbon as we make changes in the way that society regulates carbon. So I'll show you just a couple quick maps. This is a map of canopy height globally from JEDI. And so the areas where it's redder are the more mature, taller, more extensive canopy height. So you can see where the tall forests of the world are. And you can see the biomass density. So look at this. This was amazing to us when it first came out. I think of Indonesia as having some of the most amazing forests in the world, but I had not thought of them as having the densest forests in the world in that same way until I saw this map. You see the Amazon, you see the Appalachians, you can see some of the old growth forests right here that some of you will get to hike through in the next couple of weeks. And then what's really important is we can estimate the uncertainty, because if you're going to set up laws and regulations about people planting forests to get carbon credit offsets, you need to know how accurate it is, or else the whole thing becomes a shell game. And so this kind of uncertainty is really important. So what JEDI is going to do is make these measurements until 2030, but it also then is the pathfinder for the kind of laser instrument that we need to put up in the future. And right now we're trying to get that instrument in planning so that we have that future mission ahead of us. And then finally, EMIT. EMIT is a hyperspectral imager, an imaging spectrometer. So it's looking at all the different wavelengths of light. And it was actually designed to measure the dust and quantify what kinds of minerals were in the dust blowing out of different areas, so we could track global dust back to its source deserts. But an imaging spectrometer can do a lot of things, and one of the things it could do is also sense methane. So this is a methane super emission in Turkmenistan, and we've started putting out these hypercubes of these images. And then if one was in West Texas, the first thing that people did when they saw that image is they ran out to cap their pipeline, because if you've got a pipeline and it's leaking methane, it's leaking money. And so oil and gas industry doesn't want to leak methane, they want to cap it. And so this has, even images that we've had of from Iran have immediately had people run out and try to make interventions for this methane. And that's really great, because methane is the way to have the near-term effect on global temperature. Methane's about 10 times more potent than carbon dioxide, but it also only lasts in the atmosphere for about 10 years. So if we can really bring down methane, we can make a difference in global temperature right away. And so now we're working with a variety of different entities, the UN, the World Meteorological Organization, and the EPA, to try and take this information and make it useful for them to go help and intervene. So I mentioned we're developing new missions, and some of them are part of what we call the Earth System Observatory that has a set of measurements that we're making for the next generation. So these missions will launch in the late 2020s, early 2030s, and we have to be building those missions now, convincing Congress to fund those missions now, so that we have the linked set of measurements that we need to make these observations. When the missions I showed you at the beginning end their life and have to be deorbited, this is the next generation. And we try to have each of these measurements be better than the last and more tuned to the information that we've learned about the Earth as a system. And then we also have 7 Explorers missions that are going to be built by universities. It'll be a combination of university and contractors, and those will be across these 7 kinds of measurements: ice elevation, ozone, greenhouse gases, ocean winds and currents, and so forth. So I mentioned that we're trying to make our information useful. For the last 20 years, NASA's primary purpose, its primary mission in Earth science, had been to understand the Earth as a system, and we stopped right there. That was the end all. But we recognize today that that's not enough, that people need the information and the perspective we have to help them make better decisions in their daily lives. And so one of the things I've been doing over the last year is working on a strategy that you kind of see represented here. The foundational knowledge, technology, missions, and data, the Earth system science and applied research, that's what we did for the last 20 years. And we've been a driver of all the work, as I mentioned, that NOAA and USGS does by doing these things in innovative ways, doing really good engineering, really good remote sensing instruments. But now we're also thinking through, how do we make sure that the things that we know become solutions for people with societal value, whether that is information that a farmer can use, or information that a regional planner can use, or that a forest management agency can use. And also, how do we help the public understand what we understand? Because out in the media, there can be a lot of misinformation, and we want to make sure that people understand the real validated and trusted information that we have from space. We're not political about it, but we do have facts, and those facts we can explain, and we can even explain uncertainty around the things that we know and the things we're not as sure of. So this is an image of basically the latest Earthrise or blue marble image from Artemis 1. So this is where some of the things that I've been doing over the last couple years came together in that first, and that was an uncrewed mission, so that's an automated camera seeing the Earth rise for the first time into the view of the camera in Artemis. And one of the things I'm really excited about is that human spaceflight strategy I talked about that builds from things we do on the ground, things we do in low Earth orbit on the space station, things we're going to do on Artemis lunar bases, and that first human missions to Mars. Those all go together. That's actually the strategy being implemented through Artemis. But at the same time, for me, the next stage of my career is really going to be trying to come back to the beginning of my career, which was making a difference right here on Earth. So thank you so much. If you are excited about NASA, I'm going to leave this up. And so that you know how to get involved. And I am going to take a couple of questions. Bhavya, and do you have some friends to help you? Bhavya, maybe Mia. So I have 3 kinds of swag for you, which are going to be passed out while I'm answering questions. So you can get all 3. There's enough for everybody. There are stickers, there are pins, and there are tattoos. So please get those, but be quiet. And let me take a couple of questions.